Hey, natural science students, Friday here. I just wanted to talk a little bit about some of the techniques that you can use for designing a great thermal protection system. Many of you had lots of questions after we got to try the challenge 2 different times as to what could be done to really get the glue to be protected for a much, much longer time. And one way to do that is to understand the materials that you're working with and how they conduct heat. That wasn't something that we formally did in class, although I did not stop any students from researching aluminum and copper and brass. And some students asked that question, and my response was, well, look it up. What can you learn about aluminum, copper, and brass? So on the second day, I wrote a detailed definition of conduction up on the board. Conduction is the transfer of heat through a solid, and the reason why heat transfers through a solid is essentially because you are setting off a chain reaction of wiggling that is happening between atoms and molecules within a substance. And some substances are more susceptible or able for heat to transfer through them through creating that wiggling. And we have a name for that called specific heat. Specific heat is a measurement for how much energy you have to put into a substance to get it to change its temperature. And if we compare these materials, copper and brass have pretty low specific heats, which means that you don't have to put a lot of energy into them to get them to change their temperature. But aluminum has a much higher specific heat. You have to put a little over 2.5 times the amount of energy into aluminum in order to get it to change its temperature. Also, another consideration is that you can use materials other than these that you normally wouldn't work with so long as you formulate your TPS in a way that takes advantage of that. And I'm referring to air has a very high specific heat. Heat does not transfer through air as easily as it does through metals. And so what I'm going to do here in constructing a TPS that will last very long is to try to take advantage of minimizing connection points between the brass screw and the materials, and also trying to use air as an insulator to prevent heat transfer. So I'm going to pause the video and then I'll come back to it once I have a TPS constructed, and we'll see how it goes. Stay tuned. Okay, everybody, I'm back. Let's go on a little tour of my TPS. So what I've done here is I've connected the hex nuts of the brass screw to the copper screen with as little contact as I could make, and I bent it backwards, and then I bent the aluminum foil so that it is forming a large air pocket in front of my TPS. So I'm trying to take advantage of minimal connection points combined with an air pocket, air being a great insulator. And we're going to see how well this one does. This year in natural science, and it's different every year, we have most second TPSs lasting somewhere between 15 and 20 seconds. The first ones lasted somewhere between 9 and 12 seconds, and so there was frequent improvements. And then our record for this year was a minute in one of Mr. Schwenke's classes, and in one of my classes we had one that lasted 32 seconds. And so let's see how well we can do this this time around with this air pocket combined with minimal contact points with the brass screw and the hex nuts. And I have my timer right down here. Okay, and so I'm going to do what we normally do, go 1, 2, 3, start, and I'm doing this solo, so I'm going to have to make sure that I start the timer as soon as this is going. Okay, so here we go. Misfire. And the timer has started. Now, the Apollo spacecraft, one of the things that they did is that they made ablative heat shields that were designed for the aluminum to flake away. We're going to see if my aluminum shield does its job, if it's a little too thin maybe. Okay, you can see that it's glowing red hot as the heat is hitting it. And I actually don't mind if my heat shield changes so long as it stops the heat from getting through the screw. Up and stop. Okay, so we're looking at about a 38-second one. Still didn't do as good as the top student one. Now, I just want to let you know that I built that in a period of 5 minutes. I just wanted to demonstrate to everybody what you can do as examples of getting your device to go for extended period of time. And so I hope you enjoyed the thermal protection system lab. This isn't going to be the first engineering design strategy or engineering design challenge we're going to use this year. And so that is an example of some techniques that you can use to make your thermal protection system last longer.